Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Discrete Mathematics series and concerns operations on sets. This guide introduces a variety of operations you can do on sets. Specifically, it discusses complement, union, intersection, relative complement, symmetric difference and Cartesian product. It uses the Venn diagram as a medium to visualise these operations where appropriate. Introduction. The study guide, Basics of Sets, explains that there are few topics in mathematics that are more fundamental than sets. It introduces many of the common words and symbols you would expect to see when learning the mathematics of sets. If you are unfamiliar with sets, you should read that guide before continuing with this one. Venn Diagrams. This guide employs Venn diagrams to help visualise the ideas of operations on sets. These diagrams were introduced by John Venn in the late 19th century as a way of visualising logic. However, they serve equally well for looking at sets. A Venn diagram consists of a rectangle called the universe, labelled U, like this, around a number of appropriately labelled interlocking shapes which represent specific sets. For representations of 1, 2 and 3 sets, these shapes are circles, but for higher numbers of sets the shapes become more elaborate. Shaded areas highlight areas of importance. So for example, this is the Venn diagram for a single set A. This is the Venn diagram for sets A and B. You can look online for examples which illustrate more than 2 sets, but this guide only makes use of the 2 diagrams above. Example: construct a Venn diagram to illustrate a universe of natural numbers less than 10. Set A comprises odd numbers less than 10, and set B comprises prime numbers less than 10. Firstly, let's write out the sets. The universe is the set 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are all the numbers less than 10. Set A is 1, 3, 5, 7, 9. Those are all the odd numbers less than 10. Set B is 2, 3, 5, 7. All the prime numbers less than 10. The areas in the 2-set Venn diagram, this, are populated by specific elements of the sets U, A and B. This part represents the elements in set A only, and not in set B. This part represents elements in set A and also in set B. This part represents elements not in set A or set B, but in set U. This part represents elements in set B only, not in set A. When you construct a Venn diagram, you should start in the innermost part first. Here, the elements in both A and B, and work your way out. Elements in A only, elements in B only, until you are left with the elements that are not in A or B, but are in U. This gives this Venn diagram. Let's start in the middle with the elements that are in A and B. So these are odd numbers that are also prime. 3, 5 and 7. Next, the elements that are only in A. These are the odd numbers that aren't prime. 1 and 9. Next, the elements that are only in B, which are prime numbers that are not odd, which is 2. Finally, the elements that are not in A or B. 4, 6 and 8. And there we have our completed Venn diagram. Operations on sets. The following discussions are about the different things you can do using sets. These are called operations and will be illustrated using sets U, A and B, introduced in the previous section. There are many laws which govern these operations and they are listed in the fact sheet, Sets. 1. Complement. The complement of a set is the way that mathematicians describe the set of elements that are not in a particular set. The complement of a set A is written A superscript C and is the elements not in A but in U. The complement of set A is shaded grey in the Venn diagram below. In terms of sets, as U equals 1, 2, 3, 4, 5, 6, 7, 8, 9, and A equals 1, 3, 5, 7, 9, the complement of A equals 2, 4, 6, 8. The complement of the universe is the empty set, and vice versa. So, the complement of the universe equals the empty set, and the complement of the empty set equals the universe. 2. Union. You can describe the set of all the elements that are in set A or set B as the union of those two sets. Any elements that are in both sets only appear once in the union set. The union of sets A and B is written A union B and is the set of all elements that appear in sets A or B. A way to remember the symbol for union, this, is that it looks like the first letter of the word union. The union of A and B is shaded grey in the Venn diagram below. In terms of the sets U equals 1, 2, 3, 4, 5, 6, 7, 8, 9, A equals 1, 3, 5, 7, 9, and B equals 2, 3, 5, 7, A union B are all the elements that appear in A or B. So, A union B equals 1, 2, 3, 5, 7, 9. Note that 3, 5 and 7 only appear once, even though they are elements of both sets. 3. Intersection. You can describe the set of elements that are in both set A and set B as the intersection of those two sets. If there are no elements in the intersection of two sets, the sets are said to be disjoint. The intersection of sets A and B is written A intersection B and is the set of all the elements that appear in both set A and set B. The intersection of A and B is shaded grey in the Venn diagram on the left below. And disjoint sets are illustrated in the Venn diagram on the right. In terms of the sets U equals 1, 2, 3, 4, 5, 6, 7, 8, 9, A equals 1, 3, 5, 7, 9, and B equals 2, 3, 5, 7, A intersection B are all the elements that appear in both A and B. So, A intersection B equals 3, 5, 7. If A and B are disjoint, then A intersection B equals the empty set. 4. Relative complement or difference. The elements of a set that are in that set only and no other, apart from the universe, are defined by the relative complement operation, sometimes called the difference. So, the relative complement of set B with respect to set A are all the elements in A that do not appear in B. This is often called the difference of A and B and is written in many ways. A/B, A minus B, or A tilde B are all common. You should note that A/B and B/A are not equal to each other, as shown in the Venn diagrams below. Here, A/B is shaded. Here, B/A is shaded. In terms of sets U equals 1, 2, 3, 4, 5, 6, 7, 8, 9, A equals 1, 3, 5, 7, 9, and B equals 2, 3, 5, 7, A/B equals 1, 9, and B/A equals 2. 5. Symmetric difference. 5. Symmetric difference. The symmetric difference of two sets is the set of elements that appear in either set but not both. The symmetric difference of sets A and B is written A plus in a circle B and is shaded grey in the Venn diagram below. In terms of the sets U equals 1, 2, 3, 4, 5, 6, 7, 8, 9. A equals 1, 3, 5, 7, 9. And B equals 2, 3, 5, 7. The symmetric difference of A and B is 1, 2, 9. You can think of the symmetric difference as the relative complement of the intersection of A and B to the union of A or B. Symbolically, the symmetric difference of A and B equals A union B slash A intersection B. 6. Cartesian Product. The final set operation in this guide is the Cartesian Product. This differs from the others because it cannot be drawn as a Venn diagram. To understand the Cartesian product, you first need to understand the idea of an ordered pair. An ordered pair is made up of two elements either chosen from different sets or the same set. Let's consider taking an element from set A and an element from set B to make an ordered pair. You can make the rule that the element from set A is chosen first and the element from set B is chosen second. By imposing an order, you are making an ordered pair. For example, you can write your ordered pair in brackets, separated by a comma. 1, 2. This is an ordered pair. 1 is from set A and 2 is from set B. The Cartesian product of sets A and B is the set of all possible ordered pairs that can be made by choosing an element from set A first and then an element from set B second. The set is denoted by A cross B. For the sets A equals 1, 3, 5, 7, 9 and B equals 2, 3, 5, 7, the Cartesian product is A cross B equals 1, 2, 1, 3, 1, 5, 1, 7, 3, 2, 3, 3, 3, 5, 3, 7, 5, 2, 5, 3, 5, 5, 5, 7, 7, 2, 7, 3, 7, 5, 7, 7, 9, 9, 2, 9, 3, 9, 5, 9, 7. Cartesian products play an important role in the mathematics of relations. See Study Guide, Basics of Relations. A mathematical relation from one set to another is always a subset of the Cartesian product of those sets. Further guidance and information. If you have any further questions about this topic or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor or make an appointment to see a learning enhancement tutor in the Dean of Students office. Telephone 01603 592761. Email dos.help@uea.ac.uk, or you can visit our website www.uea.ac.uk/dos/let. There are further resources on many other aspects of mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills.